So what we're looking at here, ultimately it becomes a binomial distribution question, but we need to look at the language and what the clues are here. How do we know that we're working with binomial distribution? And it's actually a great example of how two different distributions can actually interact with each other, which is something we need to get more confident with. I put a little scribbled box on the side, reminding us of a few facts. These 4 assumptions, I've put them in very brief, abbreviated language, but there are 4 assumptions for a binomial distribution. And also a prompt for sort of more specific thinking about what are the objects we're counting and what property they should have. So we'll see that more clearly when we do this example. So we're told for a particular type of bulb, 36% of these bulbs become blue flowers, and the rest are white. And bulbs are sold in a bag of 40. So at the moment that's talking about bulbs. There are 40 of them, and they're either blue or they're not blue. So that's ticking a lot of boxes for a binomial distribution. And in fact, we're going to write that one down before we do anything else. So we're going to have maybe F for flowers. We don't really want to use B for blue because B overlaps with binomial. So F could be the number of bulbs out of 40, because that's how many are in a bag. So the number of bulbs out of 40, that keyword that is sort of a key point in this statement. Number of bulbs out of 40 that have blue flowers. That could be our way of describing a random variable. So a letter like F, it's called a random variable. Okay, let's use our scribbled box on the side to think about a few things. Do we have a fixed number of trials? Yes, we do. There are 40 bulbs. Do we have 2 outcomes each time? Yes, we do. They either have the blue flowers or they don't. Do we have a constant probability? Well, we pretty much do. We're assuming that 36% in the question is just a constant probability for each bulb that's selected. And do we have independent trials? Well, we're going to have to assume that we do. What that means here is not necessarily true in reality, but if you have this bag full of bulbs, you should assume that each one has its own probability, 36%, of being blue. What you might think is that actually all the bulbs in one batch might be more likely to all be blue at the same time. They wouldn't be independent then, and you couldn't use a binomial distribution then. So we're going to have to assume that they are independent to keep making progress in this question. Okay. Now underneath I said these 2 questions to prompt your thinking. What are the objects we're counting? Well, here we're counting bulbs. What's the property that they should have? What's the characteristic they should have? Well, that's whether they are blue or not. Okay, and thinking about those points is really crucial when you write down the fact that F is modelled by a binomial distribution based on N, which is 40 objects, 40 bulbs, and 0.36 is the probability that any one of them, any single one, probability that a single one has the property. What do I mean by the property? The property of being blue. So i.e. is blue. That's what P always represents. It's the probability that one of the single items has the property that, or the characteristic that you're interested in. So that's the distribution for, the number of bulbs that might be blue in a bag of 40. But then other objects come in. Russell selects a random sample of 5 bags of bulbs. And there's a probability question about the number of these bags, fewer than 2 of them, that will contain blah, blah, blah. And the sentence goes on quite far. So this is counting bulbs. So the objects we're counting has changed. So we're going to have a new random variable. Let's just go back to old-fashioned x. X equals the number of bags. And now this is out of 5, because we're told that he has a random sample of 5 of them. And what's the property or the characteristic they should have? So the number of bags out of 5 that, now we have to read it now, contain more blue than white. So that contain more blue than white. That's the property, that's the characteristic that we're asking for in these bags. This is again going to tick all the boxes of a binomial distribution based on 5 bags and a probability here that we'll come back to in a second, but it's a probability that a single bag contains more blue than white. Probability that a single bag, because bags are what we're counting, that a single bag has the property, and the property is more blue than white. Has more blue than white. We'll fill that probability in soon, but the question is asking, find the probability that fewer than 2. So it's asking, what's the probability that x is less than 2? And we know that we'll change that to less than or equal to 1, so that at the very end we can use a binomial CD function to solve this problem. Okay, so we've got this gap here, this probability that a single bag has more blue than white. Well, remember, there are 40 in a bag. So 20 blue is not enough because there'll be the same number of blue and white. So we want at least 21 of them to be blue. Now this is a question that our F distribution, the original binomial we wrote down, we want F to be at least 21. What's the probability that a single bag contains at least 21 blue? Okay. How do we do greater than or equal to 21? We do 1 minus the probability that F is less than or equal to 20. So on your calculator you can use binomial CD, so you're looking back at the F distribution, the N and the P there, and we want the probability of less than or equal to 20, and in fact we want 1 minus that probability. Check for yourselves on your calculator, you should get 0.024, and then that's actually followed by some more zeros. So 0.024. That's the probability that one bag has at least 21 blue. So that's the probability that we need to fill in the gap in this distribution here. The one that's counting bags now out of 5 bags. So we can finish what's the probability in this distribution. We need to do this calculation down here. And again, binomial CD on your calculator, you should get 0.995.